Alright guys, welcome back. This is the last video I'm going to make for lesson 5.5. I'm going to go example of an applications of definite integral. There's a lot more coming up in chapter 6, but in this lesson here, the example we're going to look at is called useful life of an asset. And we're going to try to explain this using mathematics, or at least using calculus, or the topic that we discussed in this lesson. So by definition, it said that the useful life of an asset is the number of years for an asset to remain in service for the purpose of cost-effective revenue generation. In other words, the useful life estimates the termination point where the assets are expected to become obsolete or require major repairs or cease to deliver economical results. An example real life for this, it would be, if you drive an old car, a BMW, something, at some point that car is going to break down and it's going to cost more to repair the car than buy a car brand new or buy a much, newer year of the same make and model. At some point your tractor break down and it costs more to repair the tractor than what is actually generating the revenue. Or as simple as you have a coffee maker at home, at some point the coffee maker stopped working, and there's no point fixing it because it costs even less to buy a new one. But those are just simple example. What this really saying is you have an asset, you have in terms of economics, you have an asset that generating revenue, and at some point the cost to maintain that asset is exceeding how much revenue you are gaining monthly or daily from that assets. So the point or the time at which that occurred, we call that the useful life of an asset. In mathematics, we capture that concept by saying that if you have two functions, a cost function and revenue functions, the value of t at which the costs and the revenue are the same in terms of their increasing in their rates. We capture that concept by saying that if when the marginal cost is the same as the revenue, the marginal revenue at that value t, we call that value t, or that year is the useful life of the game. In this case, the assets is a video game here, or at a arcade. So in this example, we're going to go over how to find that value of t by using definite integral. So in example 3 here, it says that we have amusement company maintains record for each video game installed in an arcade. Suppose that C of t and RT represent the total accumulated costs and revenues in thousands of dollars respectively, t years after a particular video game has been installed. All right, and suppose that the marginal cost and the marginal revenue for a particular video game is given as following. We want to find the useful life of the game and round that to the nearest year. So in other words, we want to solve for this here. Okay, so we're going to set that up. We're going to set part A, C prime of t equal to R prime of t, solve for t, and then this t is called the useful life of a video game. Okay, C prime of t is 2, R prime of t is 9 e to the negative 0.5 t. Okay, let's divide both sides by 9, so we get 2/9 equals e to the negative 0.5 t. If you recall, when we solve exponential equation that involve e, we can take the natural log both sides. All right, by doing that, it allows us to bring the powers down, and we can solve for t that way. Okay, so we have natural log of 2/9 equals negative 0.5 t times natural log of e is going to be 1. Okay, that's what we have there. Then we can finish it up by divide both sides by negative 0.5. So t is going to be natural log of 2/9 divided by negative 0.5. Now, if we do this correctly, we can round that out to nearest year. So that's going to be around 3 years. Okay, so that's the time or the year that would take for a video game after install. It will become obsolete or stop generating, the revenue more than more than what it's actually cost to maintain it. If we look at it in terms of the graph, if we were to graph these two functions, okay, our revenue rate is negative exponent in terms of power e, so it's gonna decrease like this, right? So that's gonna be our R prime of t. Revenue is decreasing over time. Our marginal cost is equal to 2, so that's gonna be a constant function. So we can say that's gonna be around here. So let's say this is 2. So this is our C prime of t. So the point of intersection here. So this is where. So let's say this is around 3 here. This is where the marginal cost and revenue are the same, right? Any time past that, any point past that, let's say over here, the cost will be more than the revenue generated by that game. So at this point here, this is called the useful life of time of there, right? Useful life of an asset. Okay. So what happened before that? Well, before that, we have two areas. We have this area here, and then we have this area. Okay. So from year 0 to 3, right, if we take the marginal revenue minus the marginal cost, we get this pink area here. So this is the amount of which the company gain or accumulate the total profit. Okay. So that's what part B is asking there. Okay. So I guess I can just make a note of that. So this is the amount profit accumulated during the useful life of the game. Okay, and then this is how much it costs here. So we take revenue minus cost, or the marginal revenue minus marginal cost. That will give us marginal profit, and then area represented by the actual profit amount. Okay, so that's what part B is asking here. Okay, so we're gonna set that up. Okay, all right. So the total profit accumulated during the useful life of the game is, okay, that total profit is the definite integral from 0 to 3 of the profit marginal functions, because if we integrate that will give us profit function. But in the previous chapter we learned that marginal profit is something as R prime of t minus C prime of t, right? So in previous chapter we learned that P prime of t is the same thing as R prime minus C prime. Okay, so now we can plug those functions in and integrate it. R prime is going to be 9 e to negative 9 e to negative 0.5 t. C prime is going to be 2 dt. All right, so we can go ahead and integrate this here. For the first function, this one here, that's going to become 9 e to negative 0.5 t. The antiderivative of e to the negative 0.5 t is going to be e to negative 0.5 t over the constant in front of t. And then the antiderivative of 2 is going to be 2t. Okay, and then we're going to integrate this from, we're going to evaluate this from 0 to 3. Okay, so today we actually another formula for antiderivative is e to the power of ax dx. So the antiderivative function of this would be e to the ax over a plus C. Okay, so that's what we use there to get that one. Okay. So now let's go ahead and evaluate this here. So equals. Okay. We're gonna go ahead and divide negative 0.5. Ooh, I think I made a mistake. That should be just the constant 0.5, not t. We're gonna go ahead and divide by negative 0.5 into 9. So 9 divided by negative 0.5. So that's going to give us negative 18. So negative 18e to negative 0.5t minus 2t. And then let's go ahead and evaluate this from 0 to 3. All right. So we're going to have minus 18 e to negative 0.5 times 3 minus 2 times 3 close bracket minus negative 18 e to negative 0.5 times 0 minus 2 times 0. All right. So what we have here is capital F of B minus capital F of A. Okay. All right. Equals. So if we do the math correctly, we should get minus 18e to negative 1.5 minus 6 minus 18 times 1 minus 0. E to the 0 is going to be 1, so this is going to be 0, so that e to the 0 is going to be 1. Then that will give us 12 minus 18e to negative 1.5, and that round up to 7.984. Okay. But the revenue and the costs are in thousands of dollars. So the value of revenue and costs, we have to times it by 1,000 to have the correct answer. So now that is, so the total profit earned during the useful life of a game is approximately 7,984. All right.